Welcome. So today we are going to see some more results about homogeneous initial value problem. Let us recall quickly the definition of homogeneous initial value problem. So here in the last lecture we have seen this homogeneous initial value problem. So it is written in this fashion that d psi dt is equal to a psi with psi of 0 is equal to x. X is in the domain of a is an operator. Okay, so that operator may not be defined on the whole Banach space capital X, but maybe somewhere inside that Banach space it is defined. And then we choose small x from the domain of definition of the operator A. Then this problem has the solution Tt of x. What is this Tt? This capital T is the semigroup generated by the operator capital A. Okay, so given a homogeneous initial value problem where capital A is given and initial point is given, one can write down the solution provided one knows what is the semigroup generated by capital A. So if we know the semigroup generated by the operator capital A, then using that semigroup we can write down Tt of x. So this is a function of time, and this function satisfies this equation that the derivative of Tt of x would be a times psi, a operator on psi. Okay, so that was the thing which we have already seen before. And then even if x is not in the domain of A, this Ttx is well defined because Tt is defined on the whole Banach space capital X. So this is still defined. So that would not be a solution, but would be a candidate of the solution. So we call that type of solution as that type of function as mild solution. Understand? Because here when x is in the domain of A, for those particular initial data, the function Ttx happens to solve this classically. But if x is not in the domain of A, then still Ttx is well defined, and that Ttx we call as mild solution of this equation. Okay, so the proof of this follows from the previous theorem, what we have discussed already in the earlier class. And we have seen one example of translation semigroup. For that translation semigroup, we have already seen earlier that satisfies this equation, that derivative of Ttx is equal to c times dd of Ttx. Okay, that clearly shows that this Ttx satisfies the equation where A is replaced by c times derivative. Okay, c times derivative. Okay, so next, if we ask that when can you assure existence of solution of this equation, then basically one sufficient condition for that would be that let A generate a semigroup, C0 semigroup, because for that we already have seen that we can write down the solution. Okay, so then the question of solving an initial value problem boils down to the following question: that given this operator A, whether it generates any C0 semigroup or not. Okay, so we are going to see one result where we are going to list down a set of sufficient conditions on A so that A generates a C0 semigroup. Okay, and that would help one to solve a given Cauchy problem. Okay, so we go next. So to write solution of homogeneous initial value problem, A should be identified as a generator of a C0 semigroup. Now for that we need some condition on A, because every operator A might not generate a C0 semigroup. So we would look for a set of sufficient conditions. So resolvent set, so here we are looking at various different definitions which would be important for describing the Hill-Yoshida theorem, which lists some sufficient conditions which assures existence of a C0 semigroup generated by the given operator A. Okay, so here this is the definition, resolvent set. So rho of A is defined as set of all complex number lambda such that lambda I is your identity operator, lambda times I minus A, this operator is invertible. Okay, so now see that if A operator itself is invertible, then 0 belongs to rho A, correct? Because then so this is invertible. Okay, and this includes all those complex numbers, for which this difference operator is invertible. Okay, so that we call as resolvent set. So we know that spectrum of an operator is contained in the complement of the resolvent set, correct? Because there you cannot invert it, correct? Okay, so resolvent of operator of A. Okay, so resolvent operator of A is another new notion which we are defining here. For each lambda in row A, since we have chosen lambda from row A resolvent set, that means lambda I minus A is invertible already. So we define lambda I minus A inverse as capital R of lambda comma A. So this operator depends on lambda and A, so that dependence is clarified here by this argument lambda and A. So instead of writing this whole notation, we write down just R lambda A. Okay, so that is called resolvent operator of A. Okay, and we are going to see two more definitions here. A C0 semigroup capital T is called uniformly bounded if norm of TT. Okay, so what is this norm? This is subordinate norm. Okay, the operator norm in the Banach space capital X. So norm of TT is less than or equal to some positive number capital M for all T non-negative. Okay, if that happens, if that is true, then we call capital TT this semigroup as uniformly bounded semigroup. Okay, so remember that in earlier lecture we have seen some theorem that the growth property of the semigroup, the norm of TT, is less than or equal to m times e to the power omega t, okay, for some positive m and positive omega. So here if we write down this upper bound where the upper bound does not depend on time, so that means this whole semigroup is just bounded by this number capital M. So here I write down omega is equal to 0 case, because e to the omega t, that omega was, so for this case you can think that is 0 here. Okay, so we call this uniformly bounded. Now, furthermore, if an uniformly bounded semigroup, okay, satisfies this condition that this norm of TT is less than or equal to 1, that means capital M is equal to 1 value. Okay, so then that semigroup is called contraction. So an uniformly bounded semigroup is a contraction if norm of TT is less than or equal to 1. Okay, so that is this case, omega is equal to 0 and capital M is equal to 1. So contraction mapping, I think many of you have already seen in other contexts. Okay, so that this definition quite coincides with that I mean, but sometimes contraction definition involves norm of Tt is strictly less than 1. Okay, so in some textbooks, so here it differs a little bit. Okay, so I am following this definition from the book by A. Pazzi. Okay, so here this is Hill-Yoshida theorem. Hill-Yoshida theorem, which I have already discussed that the importance of this theorem, because this lists down a set of sufficient conditions on the operator A such that generates a C0 semigroup. Okay. A linear operator A is the infinitesimal generator of a C0 semigroup of contractions if and only if A is closed and closure of domain of A is X. So this sentence is same as saying that the operator A is densely defined, correct? We say that it is densely defined. Why? Because where it is defined, that set is large enough so that the closure of that set is the whole space itself. Okay, so this is first condition. The second one is that the resolvent set rho of A contains the interval 0 to infinity. Okay, so open 0 to infinity, so all positive numbers are contained in the resolvent set. Okay, so in other words, I can say that for every lambda positive, lambda minus A is invertible. Okay, so for that case, for lambda positive, I can define R lambda A because it is in the resolvent set. We require furthermore one property, that the norm of R lambda A, this is resolvent operator, the norm of the resolvent operator is less than or equals to 1 over lambda. Or in other words, lambda times the resolvent operator, that is a contraction, correct? The norm of that is less than or equals to 1. So lambda times R lambda A is a contraction. Okay, so these are the conditions. Okay, then we go to Yoshida approximation. Before going that, let me clarify the implication of this theorem. So this states that if A is infinitesimal generator of C0 semigroup, then these two things hold. On the other hand, if the operator A satisfies these two conditions, then A can be viewed as the infinitesimal generator of a C0 semigroup of contractions. Okay, fine. So we are not going to prove this theorem. We are just stating this theorem. Okay. Next, we come to Yoshida approximation. Okay. What is this? This is that given an operator A. Okay. So actually, Yoshida approximation plays a very key role in proving the Hill-Yoshida theorem. Since we are not presenting the proof, I would not be able to show that how this Yoshida approximation was used in the proof. But I can actually give intuitive understanding that how is it important there. So Yoshida approximation basically approximates an operator by a bounded linear operator. Okay, so what we have seen earlier, that if your operator A is a bounded linear operator, you can always define e to the power of t times A that forms a semigroup, and there that semigroup is uniformly continuous semigroup. We have also proved that the generator of uniformly continuous semigroup uniquely determines the semigroup. Okay, so what does it mean? That means that if there are two different uniformly continuous semigroups, T and S, and then if both have the same generator, both would be identical. Okay, So that discussions, we have already seen, and that led to one conclusion, that for a bounded linear operator A, the semigroup generated by A is easily obtained, that is just e to the power of t times A. Okay, that semigroup is the one. Okay, however, in the Hill-Yoshida theorem, there that A need not be a bounded linear operator. A could be an unbounded operator. If A is an unbounded operator, we just know that norm of tt is can be upper bounded by some exponential map, but as such tt we don't know how to write down, because e to the power of ta makes no sense there. So it is very reasonable question that if A is just an unbounded linear operator, can it be an infinitesimal generator of a C0 semigroup? Then in that for that question, one can try to approximate A by a bounded linear operator A lambda. Okay, that A lambda is just a positive real number. As lambda tends to infinity, A lambda goes to A. Okay, in some sense. In which sense? Because if A itself is not a bound linear operator, then I cannot say that A lambda converges to A in the operator norm, because A itself is infinity. However, in the convergence may not be uniform sense but strong sense, like point wise. Okay, like A lambda x converges to Ax kind of thing. Okay, for each and every x, but each and every x would be also too strong, because A may not be defined for all possible x in the Banach space. Okay, so at least A lambda x converges to Ax for x in the domain of A would be desirable. Okay, so these are the kind of discussions which indicates that it is not impossible, it is just possible to actually approximate a given operator by a sequence of bounded linear operators. But then what? Then for those bound linear operators A lambda, for each and every A lambda, one can get a semigroup, and that semigroup will be uniformly continuous, and that would be easily obtained, that will be just e to the power of t times A lambda. And then you get a semigroup. Okay, you wanted a semigroup coming from A, but what you have obtained is semigroup coming from approximation of A. Okay, but then that is an approximate semigroup. But what is the guarantee that this approximate semigroup is a good approximation of the actual semigroup generated by A? So that for that one needs some effort, and these conditions are also important. So with these sufficient conditions, one can show indeed that this approximate semigroup obtained from A lambda that converges somewhere, and where it converges, that would ensure that would be the semigroup generated by the operator A. So this proof is pretty long, you understand, because it has many steps. We are not going into the details of the proof. So those who are curious about the outline of the proof, for them I just told very briefly the basic philosophy behind the proof. Okay, so we understand that the key role played in the proof is by the approximation of A by some bound linear operator. So we do that here, and we call that as Yoshida approximation. Okay, and we write down A subscript lambda here. So let A be a linear operator such that lambda I minus A is invertible. Okay, or in other words, I say that lambda for all lambda positive, or in other words, I want to say that rho A contains 0 to infinity. Correct? Because for every lambda here, lambda I minus A is invertible. Okay, so consider A is such that it has this property, the property 2 it has. Okay, so lambda I minus a is invertible for all lambda positive. Then we define a lambda by lambda. So this is the definition of that boundary linear operator, that lambda times a composition with resolvent operator of a with the same lambda value. Okay, so lambda a r of lambda a. Okay, so this is the definition of a lambda. But this definition does not immediately imply that a lambda will be bound linear operator. So we need to derive certain things to see that transparently. Okay, so another expression we are going to derive, which would show that a lambda is in BLX. So what we do is that we consider this expression 1 over lambda square times a lambda plus lambda I. So this a lambda is newly defined approximation, Yoshida approximation. So a lambda plus lambda I times lambda I minus a. Okay, so this a lambda already has lambda multiplied, this scalar multiplied. Here also I have this lambda. So this lambda come from here and this lambda here, I take common outside. So lambda divided by lambda square becomes 1 over lambda. Okay, and then what I am left with is just a then composed with r lambda a. So here a I write, r lambda a I write in the full expression of that. R lambda is lambda I minus a inverse. Okay, and then this quantity is getting multiplied with this whole thing. So lambda I minus a. And then here I don't have lambda, I just have I now because lambda I have taken outside here. So I times lambda I minus a would give me again lambda I minus a, because it's just identity. So we would be having this expression 1 over lambda times, inside the bracket we have a times lambda I minus a inverse lambda I minus a plus lambda I minus a. Now here lambda I minus a inverse and lambda I minus a, they cancel each other, and then I will be left with only capital A here. So capital A here and minus capital A here, they would cancel each other. So I would be left with only lambda I. But here 1 over lambda is already there. So only I, the identity operator, is remaining. So this lambda I minus a, I invert both sides. Now this is the left hand side, right hand side is just identity. So left hand side I would have 1 over lambda square a lambda plus lambda I is equal to r lambda a, because this inverse is r lambda a. So then I take lambda square both sides, I multiply lambda square. So a lambda plus lambda I would be lambda square times r lambda a. But left hand side I have lambda a lambda plus lambda I. So this plus lambda I take on the right hand side. So I would be left with a lambda is equal to lambda square r lambda a minus lambda I. Okay, so this is an expression, another expression. So this is considered as definition of a lambda, which does not say anything that whether it is boundary linear operator or not. But here this expression gives a very clear thing, because a lambda is equal to lambda square r lambda a minus lambda I. Okay, and here in the Yoshida theorem, in the first step we prove that r lambda a, the norm of this is less than 1 over lambda. So this is a boundary linear operator, so its norm is finite. Okay, so this is a boundary linear operator. Okay, and then multiplied with the scalar and subtracted by another boundary linear operator. So what I get as a lambda is a boundary linear operator. So this clarifies, that A lambda is a boundary linear operator. But I have not yet shown that why should we consider this at all an approximation of A. Although the name is Yoshida approximation, but it is not yet very clear that how is it approximating. Okay, so here is one special case for which we show the very basic heuristic here. For bounded linear operator A, so special case when A is itself a bounded linear operator, okay, then I show that A lambda converges to A in the operator norm. Why did I choose a bounded linear operator? Because otherwise this makes no sense. I mean, so if A itself has infinite norm, there is no way one can show that the sequence of operator converges to A in the operator norm, correct? So we take a bounded linear operator A. For that we show that A lambda defined in this fashion converges to A as lambda tends to infinity. The proof is very simple, okay? As A lambda, okay, it is defined by lambda times A times R lambda A here, and R lambda A is lambda minus A inverse, that is also written here, and then you multiply lambda inside, so then you get identity minus 1 over lambda A inverse, correct? Because when you put lambda inside, you get 1 over lambda actually multiplied inside, correct? So here that lambda becomes, lambda divided 1 by lambda is just 1, and here you get 1 over lambda. 1 over lambda A inverse, and then this A, I minus 1 over lambda A inverse, this I can write down as a series expansion. Why should I be able to do that? See, because lambda we are considering sufficiently large, lambda tends to infinity. So I can always choose one lambda larger than the norm of A. Then this would be we know that whenever I have an operator whose norm is less than 1, so I minus that operator's inverse can be written as expansion of I plus B plus B square plus B cube, etc. So we do that. We write down that I plus 1 over lambda A plus 1 over lambda square, etc. And then this A was already there outside, so we multiply A also inside, so I becomes A here, so get A plus A by lambda becomes A square by lambda plus A cube by lambda square, etc. Okay, now this if we take norm of these terms, these are decreasing, like geometric progression, GP series, okay, because A by lambda is less than 1 and the square, etc., cube, etc., those terms appear there. So so that converges, and then as lambda tends to infinity, this term goes to 0. So this term goes to, all this term would go to 0 as lambda tends to infinity. So what we would be left with is just capital A. Or in other words, A lambda converges to A as lambda tends to infinity. However, this proof is pretty simple and intuitive, but in the actual case, this Yoshida approximation works even if A is not a bounded linear operator. But then this approximation is surely not in this sense, okay, not in the operator norm sense, but in the pointwise sense, okay. So here we state that even if A is not in BLX, is not a bounded linear operator on the Banach space X, using Hill-Yoshida theorem, if applicable. Why applicable? Because Hill-Yoshida theorem requires some sufficient conditions on the operator A. If it is applicable, then limit lambda tends to infinity A lambda X converges to, so I should have written equal to here because I have already limit here. So equal to Ax for each x in the domain of A. Okay, this is the best what we can expect, because I cannot expect that I would get this equality for each and every x in the Banach space capital X, because this right hand side may not be meaningful, because A may not be defined on the whole space, whole Banach space. So wherever it is defined, there we would be able to get this convergence. So that is the success of Yoshida approximation. Okay. Now, this result this result is used also in the Yoshida theorem. Okay, so let A be the infinitesimal generator of a C0 semigroup. Okay, so if it is so, of contraction semigroup of contractions, then this A lambda, the way we have defined e to the power t A lambda, I can always get, because this is also this is an uniformly continuous semigroup generated by A lambda, and then e to the power t A lambda x, okay, that converges to ttx. So this is the part which says that the approximated semigroup is also a good approximation of the semigroup generated by the operator capital A. Okay, so for each and every x in the Banach space capital X, one gets this convergence. Okay. So a linear operator A is the, so this is another result. So we are not going to see the detailed proof of these results. We are just stating these results. Okay, a linear operator A is the infinitesimal generator of a C0 semigroup TT. Okay, which satisfies the norm of TT is less than or equals to e to the power omega t if and only if some conditions, okay, that we are going to see. Here I like to, before showing these conditions, I would like to mention that this is an extension of Yoshida theorem. Why? Because in Yoshida theorem, your semigroup was you are looking for only in the class of contractions, correct? So norm of TT is less than or equals to 1, bounded. But here we are asking the linear, I mean, when A is a given possibly unbounded linear operator, and then under what conditions on A it generates a C0 semigroup which satisfies this condition, then less than or equals to e to the power omega t. Okay, so this is a larger class. So this is infinite only if the condition is that, as before, A is a closed operator, closed linear operator. Okay, so closed linear operator means the graph of A is a closed subset in the product space, correct? So A is closed and A is densely defined, correct? The closure of the domain of A is the full space X. Second is that the resolvent operator rho A, since this we are talking about the broader class, so I have to deal with a relaxed condition here, correct? So rho of A contains the array, which array? That the set of all lambda in the complex plane such that imaginary part is 0, so that means these are all real lambda, and lambda is greater than omega. Okay, so for omega onward or more than omega, so rho of A contains omega onward that ray. Okay, for such lambda, that means for lambda which is in this class, the lambda greater than omega. Okay, so the norm of R lambda A, so if we choose this lambda from this set, the norm of R lambda A is finite. So this is a boundary operator. Not only that, that is less than or equal to 1 over lambda minus omega. Okay, so this is extension of Yoshida theorem for contraction. Okay, so generally when we say Yoshida theorem, we also sometimes refer this a whole collection of theorems. Okay, now consider. Okay, so we need to talk about a little bit about some examples, otherwise things are becoming a little more abstract. So consider the space V. V is a set of all functions f, real valued function R to R, which are bounded continuous with the sup norm. Okay, superior norm. Consider the translation semigroup. Okay, translation semigroup given by TT of f A defined as f of A plus C times T. Okay, so this is translation semigroup. We have already seen the definition. Okay, so this is defined on V, which is defined on V. Okay, so then for this particular semigroup, we can ask that is it a contraction? Yes, it is. We can show that norm of Tt is equal to 1. How do you show that? See, we'd consider f from, with norm of f is equal to 1, like, unit sphere of this V. So that means where supremum of f is equal to 1. So in that case, Tt of f, if we take the supremum of that would be same as norm of supremum of f of a plus ct, because when we take supremum, we range a over all possible real number, so that anyway covers a plus ct also, doesn't matter what t you have chosen. Okay, so norm of supremum of Tt of f is same as f of a plus ct, norm of f. So operator norm would be just 1. Okay, because norm of f I'm choosing, on the unit sphere of the Banach space, that norm of f I'm choosing 1 only, so I'd get 1 here. So thus the translation semigroup is a semigroup of contractions. Now the generator of the translation semigroup, we have already seen earlier, is constant time the derivative. Okay, so this derivative operator is surely not defined on the whole space V. Why? Because this is space of bounded continuous functions, so all the members need not be differentiable. So this derivative is not defined on the whole space V. So this operator is defined only on the space set of all functions which are differentiable. However, this operator is densely defined. Why? Because every bounded continuous function can be approximated in supremum by a sequence of differentiable functions, correct? Even if we have a very sharp points where it is not differentiable, we can have a smooth version there and can keep it very close to the supremum. I can decrease to 0 as the sequence progresses. So that is the comment here, that for this particular example, this is the way we understand that the operators are need not be defined everywhere, but is densely defined. So this justifies the conditions what we are talking about here, and the concerns what we are keeping in our mind, the relevance of those. Okay, next we come to theorems on homogeneous initial value problem. Okay, so these two theorems are taken from the Epaz's book. So I have written down the page numbers of the book of this theorem in the book, so that the curious students who would like to see the detailed proof of this theorem can refer to this. Okay. So let A be a densely defined linear operator with non-empty resolvent set. The initial value problem ddt psi is equal to a psi and psi of 0 is equal to x, that IVP we call, has a unique solution psi t, which is continuously differentiable on close 0 to infinity for every x in D of A, if and only if A is the infinitesimal generator of a C0 semigroup Tt. Okay, so what is the difference between this theorem and the theorem what we have already quoted? The difference is in the earlier theorem, what we have seen that if A, this operator A generates a C0 semigroup, then that constitutes a solution of this initial value problem. But this theorem says the other side also, is the if and only if thing, that this equation has a unique solution psi t, which is continuously differentiable. Basically, it's talking about the classical solution for every x in the domain of A, if and only if A is the infinitesimal generator of Caesar semigroup. Okay, so that means that if A is not an infinitesimal generator of a C0 semi-group, we cannot, I mean, this equation does not have a classical solution also for X from the domain of A. So remember that here for this theorem, we really require X to be in the domain of A. If X is not in the domain of A, TTX does not solve it. It is considered just as a mild solution. It's not a classical solution. Okay. Okay. So next, I go to the next theorem. So this appears in page number 104. If A is the infinitesimal generator of a differentiable semigroup, so here we are putting more condition on the semigroup. Okay, a differentiable semigroup. So that means it is a very restricted class of operators. Then for every x in capital X, since we are choosing only a very special type of operator A, so we can get a nice result. That is that for every small x in the whole Banach space capital X, the IVP has a unique solution given by TTX. Okay. So this is as expected that of course if we select from a smaller class we can get a better result, but this is the theorem. Okay, so what is differentiable semigroup? That means TTX is that is differentiable. Okay, even if the semigroup generated by A is not differentiable, okay, so then we cannot say say that okay, TTX is a solution, but one can surely define TTX. Okay, even if A is not differentiable, one can surely define TTX. Then that TTX would not be a classical solution, but we call that time TTX, is a mild solution of the above initial value problem. Okay, which need not be the classical solution. Okay, thank you very much.